Shivappa sir?
Yeah.
Yeah. Now see the basics no of digital design. I think
Yes.
what feedback I got from the participants that we can skip those basics. They are interested in FSM, actual FSM design using Verilog, analyzed state machine using Verilog. So like the things which they might have studied earlier in the digital design, no, you can little bit either you go fast or means skip like that. They would like to know basically how to design the FSM using the Verilog. That's what I got the feedback. Hello, so your voice is. I could not hear you.
Use okay. 1 minute.
So your voice is breaking. I can't hear you. Shilpa, your voice is breaking. He has to restart the system. His system is hanged. That's what he's saying. He'll be restarting the system.
Hello, can you hear me now? Am I audible?
Yes, sir. Yes, sir. You are audible.
Okay, okay, we'll go ahead. See, one thing I heard that you wanted assertions. Assertions.
No, not assertion. No, no. I was not talking about assertions. I was saying that these digital fundamentals, no, like
No, no, that anyway
you
I'm
directly
skipping.
go
No,
for
no, no,
coding.
that I'm skipping. You asked for state machine. I wanted to start with the state machine. Do you want
Yeah,
state
yeah,
machine or not?
yeah, 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 yeah. We want state machine coding in the Verilog direct. Okay.
Okay. Yes, yes. So that's what because
Yeah,
morning you told, and I wanted to start with the state machine now. Okay.
yeah, yeah, yeah. Okay, okay. Go
Yeah.
ahead, please.
Can you please give me the share access, share content access? Yeah. Sorry for the inconvenience. Somehow system I had to reboot. Okay. We'll start uh, this machine. So I think, and I'll cut down some of this basic even explanation because looks to be, many of the faculty members knows about the state machine, right? The use of and where they are used, right? So basically, right, where final state machines are used. So everything, right, you have to process things in sequence. And so that's where you deploy the final state machines. In the design, there are two parts. Always there is a data part and the control part, right? So the data, it's the flow of data from inputs to the outputs. The control part, based on certain conditions, right? You have to pass those controls to the data part, those decision making, right? That is, the control part is specifically implemented using FSM. So graphically, you can represent using state diagram, right? And you will give a certain, name. You represent each, state using, the unique configuration. And one state to the other state, we call that as a state transition. And now the transition is based on certain conditions, right? Those are based on certain inputs, right? And the transition conditions. And now in each state, there has to be some action associated with the given state. Okay. Now let us take an example. Now the CPU, if you look at, it's a 4-stage or pipeline access. So there is a fetch, there is decode, there is execute, there is access. There are different, each cycle, it has to do certain functionality, right? So now this one, right, you can better represent using FSM, right, on reset condition. After that, the first state is fetch, next is every instruction has to go through this sequence, right, and decode and execute and access, right, and then further, then again it goes to the fetch, it goes to fetch the next instruction, right? And now this is state, and these are the inputs, and the transition from reset to fetch or fetch to decode, those are state transitions, and this is state action. So what you do in this state, actual fetch happens in this, that is an action in this state. There are two types of state machine representations, as you all know. One is Moore state machine and other is Mealy state machine. State machine is represented like this: inputs, next state logic, and state registers, and here the output logic. Okay. Now output Y is a function of the present state. Now what it means is these outputs are dependent only on present state. Output Y is a function of this state vector, right? The present state vector. Now here, what to note here is these outputs don't react immediately to input change. Now there is some change in the input that will not get carried outputs here. So in other words, outputs are only sensitive to the state here. What is the advantage with this? Okay, you can refer back to the latch and the flip-flop, the waveform I was explaining. Moore state machines effectively filter out transients. Now, any noises or signals or any small changes happening at the inputs, right? Those are not getting passed to the output, and they are getting filtered out here itself in the, and then because this is coming further from the state register, there it will even out any transient which are happening at the inputs. Okay, and that's how it can be used to eliminate any glitches or the race conditions. So diagrammatically, if you want to see this, put, and this is next state logic, this is next state logic, and the state memory, right? This state memory is the state register, and this is output logic. This is output logic, right? If you look at this, depending only on the state, the states. So this output stage. So in other words, this is not connected to this state. So that's about Moore state machine. Mealy state machine, how Mealy state machine is different? Look at. Now there are inputs, next state register, output logic. Only changes inputs are or outputs are dependent on present state and the input. Okay, so that is the difference. Okay? And output is a function of state vector and the input. So with this, what is the change? Outputs react immediately to input changes. Whenever any input changes, now output also changes. So Mealy state machine are used to create control blocks that respond quickly to the external signal changes. So now with this, you have to make sure that you have to isolate this output logic, which are sensitive to the transients, right? So that is about the Mealy state machine. Now, if you want to represent in the diagram the same, this is next state logic, state register, and this is output. So this output stage is dependent on the inputs as well as state, present state. Now, the state representations, we use different encoding schemes. So we use binary encoding, we use gray encoding, we use one hot. Okay. So what is the difference here? Normal binary encoding is what you use. Gray encoding, if you look at from one state to the other state, as you know, there is only one bit change, right? And where power critical applications, you can use gray code for implementing the state machine encoding, and binary, in normal cases, and one hot encoding you can use in FPGAs, where only one bit is changing, not changing, one bit it is one hot. One hot means it is one bit is high, active, all other are zero. Okay, so that way each state you can represent using any of the. What it says is synthesis tools use their built-in optimization to detect the best encoding schemes. Okay, so when you synthesize, it will optimize the logic based on what you have used. Okay, so now how do we write the state diagram, right, for this Mealy and more state machine? Now, a simple example in order to write the state machine, taken you have to detect a sequence of 1, 1. Okay, this is more state machine. Okay, so if you want to detect 1, 1, you need minimum 3 states, where one is this how we represent, you note here, this is the state, this is the output, and this is input. Okay, these are inputs, and here this is state and this is output. Now, first state A, output is 0, and now at the reset condition, let us say when this is in this state, when the input is 0, right, it will be in the same state, because what I want is 1, 1. When 1 is detected, when the input is 1, it goes to next state, and then that state is B, and output is still 0 because I detected 1. Okay, then from here, when this is in this state, when it gets 1, it goes to next state, and it got 2 1s, and output is set to 1, and the state is C. Now, what if in this case, if it gets 0, right? If it gets 0, so 1, 0, and again here it is going back to A state. Okay, and now once it has achieved, got into this sequence 1, 1, Again, again one comes what? It will be in the same state, right? So these two ones, right? And if 0 comes instead of this one, right? 1, if it is 0, it starts from 0, right? This is how you can understand the Moore state machine. So the representation. So you usually see that one extra state will be used for Moore actually. So you want to detect 2-bit sequence, you're using 3 states. Okay, so now that is the same what I explained is shown in this table: reset, input, current state, next state, and the output. Now Mealy understand in the same way. This is how we write. State only we put in this box, right? And this is input, this is output. Okay. So now in this state, when 0 comes, be in the same state, right? And output is 0. When 1 comes, output is 0, and this input is 1, right? Input is 1, output is still 0. Now it goes to next state. Now in this state, again one more 1 detected. Now 1, output is set to 1, right? 2 ones detected. And so this also means if you look at here, this based on the input immediately, the output is changing here. When it is 0, here, even from this onwards, now again it goes back to the initial state. Okay. So that is how Mealy uses one state less than the Moore here. Now I write, let us try to write the code for this. Okay. Moore state machine code, the same what I explained. So this is how we write. Okay. Moore state machine. What are the inputs? It is a sequential circuit. Clock, reset, and D in is the input and output is D out. Okay. Now what is D out? It should be 1 when 1 sequence is detected, output should be 1, right? That is what is output, and input what I'm expecting. It may, you may get some sequence 0 1 1 0 1 0 1 1, whatever. Now whenever you detect 1 1, you should see this output as 1, and whenever 1 1, you should see the output as 1, right? That is the intent here, intention of the program. Now parameters are used in order to represent the states. So now Moore state machine, now 0 1 2. Now you know that there are 3 states, and then I have given 0 1 2 3 1 2. And as you know, there are 3 states. How many bits you need in order to represent the state register? You need 2 bits minimum, because there are 3 states. So with 2 states, you can represent up to 4 states. So that way I need here 3. Okay. And state transition. Okay. So now the states I declared, what are the states, and the state I declared. And now how every cycle things I have to see. Now at passage of the clock or the reset. Now if reset, the state has to be in S0. Okay, this one. And just diagram. The moment you write the correct diagram, then the coding will be easy here again. Output will be 0, D out will be 0, right? Next, the program continues. Now, case statement, you're putting state when it is S0, right? This is reset condition. And this is S0 condition. When in S0, D out is 0. If D in is 1, means if D in means is checking if Dn is 1. Okay. State is S1. Now it is going to this state here if Dn is 1. Okay. So this is one case. If it is 0 case, it will be in S0 only. Okay. So now here every clock it enters. Now the next clock is S1 because here you have assigned state is S1 and next time S1 is assigned at the end of this time unit. Next time when it comes has been assigned, that is non-blocking. Okay. S1 and here in S1 again D out is 0. Okay. And there you check if D 1, it is 1. Then go to S2. Go back to 0 here. So now this is in the second cycle. Now further, depending on this S2 or S1 seen, next time state 1. Okay, output is 1 here. And if D in, here you check if D in is 1, then B in state here. If it is 1, B is 2. Yes, go back to initial state. Okay. Of course, in the default, any other cases, D out make it 0, then keep it in the initial. Because it is happening with respect to the clock, right? And with respect to the clock, now you see that the inputs and outputs clock, reset, D in are the inputs. A simple test bench here. Out. I instantiated this connected clock reset in and out here. Initial begin reset clock, all I initialized, waited for 5 time units per. So then this I'm making it 0. Yeah, because this is active high reset. When reset, then it is going to reset. When it is 0, then it's out of reset. Okay. For 100 clocks, I am generating simply random number and assigning to in, so that the bit stream of 110 whatever it is generated and then assigned driven to this input. Okay? Every clock at any point in time, if the out is 1, the pass sequence 1 is okay. Whenever output is 1, okay. That anyway further we can out 1 only when sequence is detected. If when sequence 1 is not detected and then still output is and finally after assigning sending so many patterns, then wait for this much time and dollar finish. And of course you dump the waves. Okay. So more a state machine. And if you to verify, you can follow this approach. Okay. So any doubts here? Is it all going good? Able to understand? Is it clear?
Yeah, it is okay. If anybody wants to ask anything, you can ask. You can discuss.
Um,
Shivappa,
so what we do?
okay.
So I will explain about the Mealy state machine also. You will know hand in hand, and then we will get simulation part. So if I want to show you the output here, this is the clock, this is the reset, and this is the input sequence, and this is the output. And here, every clock, right? So now this clock edge, it detected one. This clock edge, it detected one. Actually, in the next clock is where output is asserted. That's where we call this registered output. Okay. And then again, if you look at previous ones, right? So here, because this is input is one again, one, right? Up till here, you see this output is one. Now in this cycle, you see that there is going low because input is changed to zero. And again, it will look for sequence one here, and then you see this output going one here. Okay, and then further again zero. So if you look at the pattern, see, it is clearly output is going to it is setting to one after detecting two clock cycles, and this is because it's one more state extra. You see that the output is in the next clock. Okay, so this output is coming. The one was detected here, but in the is where you are getting the output. Okay, that is what is the different. You can select very, most of the time Moore state machine is good, though you are using additional gates. Mealy state machine where input transients filtering is not happening, so that way Moore is more uh, used actually. So nowadays, this kind of optimization techniques and all that is at the coding level, right? The more of optimization shifted to the backend optimization and device manufacturing level than at the design level. So earlier, when you are writing code, you wanted to write a very optimal code where you
So,
wanted to reduce the logic, reduce number of bits. Nowadays, synthesis itself, based on some effort level, it will optimize and minimize the gates. And more of things are happening or moved to the tools level than designer bringing more of optimization. So nowadays, so that's the thing. Of course, with these
Shiva,
advantages, disadvantages, whatever, you can always
yeah.
see what is more suitable for your application.
Shivappa, excuse me, Shivappa,
Okay. So
hello, Shivappa,
now the same
that,
sequence, right? This is Mealy station, and uh,
Shivappa,
we
hello,
use
sir,
only two states here. Okay, I started as
hello,
one, and the state and the next state register, and then here state is S naught, and else. See, I used the state transition separate during reset test state is zero. This is another way of writing the code where there is always block for state, and just for state transition you have one a block, one always block, right? And then here whenever state changes or input changes. See this? This is the difference when you are writing the code bringing to the Mealy circuit. So now state in S0 output is 0, then if D in is 1 and then S1, right? Else it is S0. Come S1 if this is 1 and next state is S1, right? And output is 1. Okay, and then else go to S. Okay. So that is there are only 2 states for the Mealy, and then this is default case. With the
Shivappa,
same test bench,
hello?
you
Hello?
outputs are same. Same test bench can be used.
My voice is
Verify
not
this Mealy circuit also. The test bench, because input outputs are same and what sequence you want to do is same, right? Okay. So here just the design I included, and I just the typical test bench structure. So based on this, now we discussed about the state machine and the code, right? The circuit, the realization based on the truth table, right? You can look at the optimization, and there's one example given inputs and outputs next state, and for a particular sequence. So that way you manage using K-maps, simplify, and bring in this logic optimization. For D0, you find an equation. For D1, D1, you find an equation, right? And then finally this output logic based on the Mealy or More, right? You put with this part. So this is a Mealy or More, this one. The Mealy circuit. Okay. So now you can also look at some complex examples detecting a sequence 1010 and non-overlapping. See, there I took overlapping case, right? So here non-overlapping, if you want to use, always non-overlapping means you are trying to get 10101010. So basically 1010 and 1010. So basically you don't want this 10 to be considered for this thing. So this will become overlapping, right? So we don't want to consider after this start from the 0, right? Now this is non-overlapping, right? 10 like that. If you go non-overlapping, this is overlapping. So those things are considered and design state machine. Okay. So non-overlapping case, this is using Mealy, right? And I put out both the state sequences, and then I'll tell what is the difference here. Okay. So what is the difference here between the non-overlapping overlapping 1010? If you look at 1010, right? After 1010, it has to start from 0 again to detect 1010. Okay. So now overlapping case here 1010. Now again it can start from S2, that is 10 can happen, right? So after S3, instead of the next state being set to S naught, you can set to S2. Okay, so that is the overlapping case. So this is Mealy. If you look at the Mealy circuit 1010 non-overlapping case, see this here, non-overlapping case 1010 clock. Now this is D input and the reset is 1, right? So the next is the D out is output here. So overall 1 0 1 0. So immediately it has changed. Output has changed with respect to the input. Now again you set it 1 0 1 0, right? And 1 0 1 0. So this is non-overlap. So if you look at the overlapping case here, you can compare here 1 0 1 1, right? Then the next sequence, right? It starts from here 1 0 1 0, right? This is the output. Now here you could see this. So you can relate this non-overlapping and then overlapping. Now this is the circuit for sequence detector using the code. So that what I explained. So that's where the moment you have a state machine in hand, you can create like state machine code and then similarly if you want to do the Murray state machine, see this 1 0 1 0, one extra state, and it's going to S1 here. 0 means it goes here, 1 means it goes here, and then here if you look at it goes to S3 because 1 0 1 0, right? Now again if it is 1 1 0, right? So that's why it's connected here. So same way how for example we wrote, you can simulate this actually. See this simulation, right? What stimulus you send to the drive to the DUT, right? So you're modeling here and then drive. So if you look at this is 101 D in 0, right? And this clock. And let me see this 101. So this is 1010. So because it gives next clock here, right? And in the next clock it gives. So one clock further it shifts actually. So here, if you look at the overlapping case, here also you see this. It alternates actually. So here 1 0 1 0. This output is coming here, and then next overlapping is 1 0 1. Sorry, it counts from here 1 0 1 0. You get here. Okay, then 1 0 here. So it counts from here. This 4 leads to this output. So that is about the state machine. One thing we can do is we will simulate. So any questions you can always ask. how many of you got access to the tool? Okay, I'm just cleaning up. State machine here itself I will run. Let's see Verilog plus access so WC minus level sequence detector. Okay, so now the same code what I simulating. So now that is the those are the messages you get. Um, in the limit here. So open the simulator waveform. Just a minute. Okay. Let request. Okay, so now I just checking whether I have dumped the signals. So dump.vcd is created. Okay, just for a change, I have generated VCD. Okay, so how to open VCD in this file? In this one, we will see open database. Look at this. By default, trn file is what it says. Select VCD files. .vcd. Then it will translate this VCD file into its own native format. Now you say okay, so it has translated VCD to trn file. Okay, now you can look at how these are the different states, and d in and d out. You can look at based on the clock. Right? So whatever in the document I explained, right? This state keeps change 0, 1, 2, 3, 4, 3, 4, 3, 4, whatever, right? Because it is overlapping, right? And it is continuous output. So if you want to change the stimulus, for example, for some time you give a different value, right? All those you can try in your program. For demonstration, we just created an ideal case here. So let us say sequence detector TV.v. So you can change, for example, this in this. I'm complementing this input every time. Okay, and let me try corrupting this actually. Whether it will, what kind of this thing it will generate, we will see. Okay, now you can open, you can reload database, hopefully. Stimulus is not changed. And look at changing values. What I did is state machine %. See now less number of sequences. Let me see with the waveform. See that TRN file is previously translated one. So now VCD again you need to translate. Okay. Now if you look at the input output, see this. I just randomized and I didn't give ideal case continuously 1010. I gave random values, right? So if you look at this one, see here all ones, 1, 0, here 1, 1, right? It is not 1010. And here if we consider from here 1010, right? No. So if you look at here 1, it is considered from here. Okay, 1, 0, 1, 0, and then he has given output here. Okay, and then 1, 0, 1 here because it's overlapping, right? He has given here. So that way, actually, you can play around with the stimulus. So you can take the Mealy code also, you can execute. That is also working code. So that is any other things I have in my presentation about, yeah, this thing state machine, that's all what I had. So another 1 hour is there. I will just leave it open to you what topic you want to discuss.
Okay.
So there are.
Hello.
If you have specific thing, please let it come from you. Otherwise, I will suggest
Ma'am,
what
please
would
go ahead.
help you. What
Yeah,
topics
yeah.
would help you.
Is it possible for you to throw some light on asynchronous machines? Asynchronous. Hello. Can you throw some light on asynchronous state machines? Asynchronous designs.
Hello, I'm not able to hear.
That is the problem.
Are you able to hear, Rathod?
Yes, ma'am. I think he's having problem. That's why in between I was shouting, so he was not able to hear. Shivappa,
Hello. Rathod sir, you're talking?
Yeah.
Yeah. Is it possible for you to give some details of asynchronous machine? ASM, asynchronous state machine.
Here will write in a chat box to him.
He says, I am not able to hear.
We're able to hear you. Will write. I'll write.
1 minute. Can you hear me now?
Yeah.
No?
Can you hear me? Yeah, we can hear you, but are you in a position to hear us? I written it in the chat box.
I think he's not able to. Privately write.
I think he's not able to.
No.
I'll
Can you hear me?
Yeah, no, I can. Yes.
I think it was getting muted. Okay. So what I was saying is, now these are the standard practices. This is the way how we use asynchronous state machine means, see, anything the state changes has to be happening in sequence, right?
Uh,
Now asynchronous means what? Now anytime anything can happen, right?
yeah,
And
there is
you
no clock
that
input.
with
There is
sorry.
no clock input. There is no clock input.
Without clock input. So now you just have your if else statements, and then you see the values, and again the moment you say you are not using clock, memory is lost. Now you are not using memory. Right? At least latches and flip-flops are the ones which are making you to remember the previous states, and then moving on with the next state, right? So that way there is see Mealy and then More itself is good enough for all our this.
Okay, so most of the designs are using synchronous finite state machines only.
Yes, very much, no doubt.
Okay.
So I have to interface this online cadence access is available all the times of the day. No, that, yeah,
Shivappa,
yes.
I can understand that there is a different tool for synthesis, but can you show something on synthesis? Because without looking at synthesis,
So you want to see how synthesis happens.
because if we have time, then that will be good, no? Because synthesis of this, even if you can show machine state machine, synthesized state machine, it is there.
Let me see if some examples are there handy. I can show that.
I think Rathod sir.
Madam, bola.
Yeah, I think all the discussion since yesterday is on the behavior or the functional testing only. There is no
Yes.
hardware content into it. So how it goes to the layout and finally gets implemented in silicon, if it can be shown with cadence tools, I think that will be more from VLSI design point of view.
That is what I am asking him, if he can show synthesis, a small example.
Yeah, correct.
So this code he has written, if you can synthesize and show,
Yeah,
and then the participant
whether
will be
that
more.
code can go finally after synthesis to the
Yes.
placement routing and all that. Yes.
Yes. So
Yes.
flow, one example and flow complete. So
Yeah, correct.
yeah.
No,
Shivappa,
see,
sir, are you hearing?
No. See, that is correct actually, but that is not a fair expectation. And it's 1 hour. So
You
we
don't. You
confined
only show through one example.
Yeah,
Through
no. See, that is what is this thing actually. See, we maybe if you want, you can set up some other day a PD flow synthesis, STA, static timing analysis, and the PD flow. We have complete, separate this one, right? We can take one design. It could be state machine or anything, and then we can walk you through and with the tool, cadence tool. Okay, so now only the functional simulation. I'm not even touching for gate level simulation. So gate level, we contain all our discussion for the functional. Here also, I'm not seeing some of the examples because we moved to the different server. If in the old server, all we had some work there. Okay, so we would have done it. Now, so we don't have the examples created here. So that way, I'll not be able to demonstrate here. So maybe some other time we can do that. It's not a problem taking one design and then synthesis maybe 1 hour we can do, and then maybe PD flow definitely it will take. See, PD flow placement, floor plan, routing, right? All takes time. Just for presentation, okay, this is how it looks and all. So when you want to do this, you'll have
But
to set aside at least half day.
Shivappa, sir.
Yeah.
I think we personally had not interacted. I had interacted with Swapnil and Damodar about this workshop in detail. My expectation was you will complete from start to end everything.
No. That if that was the expectation, right? I don't know. That is not communicated to me. It is pure Verilog is the expectation. What was shared with us.
Okay. Anyway, now whatever you can do, you do. Otherwise, let it be. Then we will have a break and then we will meet at 5 o'clock in that case.
Yeah. So one, see, for example, now protocol-based designs are there, and 5.4 design is there. Couple of designs, if you are interested, we can walk through, and I can show you the code coverage, those aspects, right? And which is of interest in the front end actually. So if that is not exciting for this audience, it's your call. So see, if you look at see this digital design stages, modeling using Verilog sequential logic guidelines, right? And design of state machines, memories, and functional verification, right? So
Okay,
protocol,
you do one thing then.
right?
I'm giving a middle solution. One thing. Can you show the code coverage? A simple example. Don't explain a lot of background, but through simple example,
Okay.
how
And
code
I will
either
just directly run with the code. For
Okay.
example, now the state machine itself, I will run with the
Okay.
code coverage. I will show you.
Yeah, exactly. So what exactly is the code coverage? That we will explain in the we will see how to cover that. Let us say tomorrow or day after tomorrow.
Okay.
That we will do it on our own. You
Yeah.
just show right now the example. That is, I want to execute. I want to see the code coverage.
Okay.
How
No
much
problem.
code has been? Yeah. You just show that. So participants, you just pay attention now. Okay, we will have in some other session what exactly code coverage is, but then how to run it through Canvas at least.
See, when you want to simulate, use minus coverage all. So now minus coverage, it is the command what we are passing to the simulator to capture the coverage. Okay. And what is this all means? You have different coverage types.
Sir, Shivappa sir, are you sharing the screen?
Oh, did I stop
Yeah.
that?
You are not sharing the screen.
Yeah. Yeah. Now it should be okay, right?
Yeah. Okay.
So now look at this, the command. Let me clear the screen. One moment. Okay, I don't know, for some reason it doesn't work. Okay, so what I was see, this is the simulator command which we were using. Now, if you want to run with the coverage, you say minus coverage, okay, all. So what is minus coverage means? It will enable the simulator use this option in order to capture the coverage. All means you have different types of coverage, say line coverage, expression coverage, right? Branch coverage, those kind of things. So now you want only expression, you can give some EXPR. There are each simulator uses its own this one, right? So you can specifically, now I am selecting all, okay, and rest all same. Okay, now if you look at so far, it had not generated any coverage information. Okay, and now with this, it should capture the coverage. Now here, coverage setup. Earlier simulation, you are not seeing this work directory. It created cow work, and then in this DUT instance and scope and the test. So what it has generated, go to cow work. Just like Encoding for the simulation database, here coverage database is available here. Okay. And now this UCM file, it creates, see all this, it is for its use, UCM, and then one more file is this UCD. Okay. So these, its own format, UCD is what we use in order to see the coverage. Okay. So all this is dumped in this UCD and then UCM file. So now next is, I just like SimVision, I opened in order to see the coverage information. I open IMC. So this is incisive metric. Metric C is for some calculation or whatever. So now this, it opened IMC, right? And the center, incisive metric center. So metrics is what one word we use for collecting the verification metrics. This is one of the verification metric. Okay. So now load data, cow work, scope, test. Okay. Now this one is the one what you are loading here. So when you load it, you are seeing that verification metrics, types, instances. Now this is the test bench and the DUT. Okay. So overall metrics, it is showing 89%. Okay. And this types, if you go, this is more, and this design, and then this is test bench. So usually we capture and then analyze code coverage for the design alone. Okay, for the design alone. If you look at this More and the DUT instance, it is 90.67, 90.67. Okay, here what to note. If you select this DUT, you look at overall code coverage in the code block expression toggle. FSM is there, right? FSM coverage. Actually, there are no expression. That's how you're seeing not available. Functional, this is what comes into picture when you code functional coverage, that is in system Verilog. Right now, this is not applicable. So even when you're dumping the functional coverage, you use just the coverage option what we used here. So now this one, let us say toggle coverage. Now I have selected the DUT, right? And then toggle coverage. Click on that. Now toggle coverage is what? For all the inputs, right, and the outputs, it looks for both the values 0 and 1. For example, clock, anyway, it is changing from 0 to 1 many times. This is captured. Reset, if you look at right from beginning, I think reset, I have made it only one value, right? So that is where it is showing 0%. Okay. So reset is not toggled. That's what he's saying. And D in input is toggled. This is only toggle 0 or 1. Okay. The input is, for example, now reset. See, it is always score is 0 and it is not toggled. That's what he says, right? I think right from beginning we have fixed the value of reset to only one value that we will see. Now, when you look at this kind of hole, these are called coverage holes. Now you need to toggle the reset. Okay. And that how can you do? From the test bench. Okay. Now it's a measure of verification, right? So I am little bit withholding myself giving more explanation, right? And more these things you wanted. So now further, this is about the toggle, and next. Where is that? Yeah, here. Cancel. So go here. Yeah. So yeah. Okay. So now you can look at the next part. Yeah. So now I was looking at toggle, right? That's the overall score. It is showing 85%. Now go for block coverage. Okay. Block coverage. See this? Now it is showing the block coverage. What are the blocks which is highlighted line by line? See this always block, right? Else block, and then this case, right? And it will consider begin to end is one block like that. Okay, this begin to end, right? And the condition is will be all conditions will be covered in the conditional coverage, but it goes by block. Okay, that's the block coverage. And what is, for example, now false part of this one? See this false part of this is not covered. A case item of this is not covered. Okay. So like this, you can identify the coverage holes, and then we need to look at this non-overlapping. I think only one we have. I think we have created overlapping. non-overlapping we have not simulated, right? So that way, this is missed. So like this, you can create this. This is about the block coverage. And next is expression is not there. And FSM, specifically of our interest. Click this, see how it gives. So it also shows S0, S1, S2. This is how the state diagram looks. Okay. And yeah, so this code, it also shows, right, how many times this has transition arcs. So this one thing which is not covered. This is a bubble diagram. Okay, so this is the state, this coverage, the state machine coverage. So if you look at similar thing, if you go for the functional coverage, you can analyze the functional coverage whenever you have run with this one assertions for checking protocols and other things. So in system Verilog, we model these coverage groups actually. So, and overall, it calculates the percentage. For example, how it calculates, these are the goals. Right hand side is the goals, 39 out of 39, only 35, right? And 26 out of 26, 23. So like that, it computes the percentage. Okay. So now really, if you want to see that reset part, you can just try to toggle it and then see how we can address that also. For example, other way is you go to designer saying that is designer says that is an unintended case, right? That the design should never enter that particular line or state. So then you can use something called exclude here. Okay, exclude local, exclude only the local aspects of the instance, and then you exclude those particular lines. See this, I am completely excluding this complete DUT actually, right? And unexclude. For example, now in the DUT toggle itself, we were looking at it. Let us say this reset, and here if you say exclude, then you will show 100% actually. Now this, you're saying that is not a coverage point of my interest, and then you better exclude from my coverage. Your percentage calculations will improve. Sorry. So now you see this here, your percent, what is your overall grade? 90.61%. Now when I exclude this, right, see this, your grade went up to 94.24. So similarly, the states which you have seen and not entered, if you exclude, then you can make it 100% here itself. Okay, because you are saying that okay, that is not coverage of my interest.
But Shivappa, then don't you think this is a wrong methodology of adjusting the coverages in this front end?
No, no, no.
How it is helpful? How it is helpful?
No. So it is, I am not saying that this is the way. See, let us say in the state machine, the example is this default. Let us say designer has put default, and this default, it should never enter. Now your simulation also has not touched that, and designer also should, that it is an extra code what I have put in this particular version. This is not going to be used at all. Then those lines, right, are those if else cases you are excluding, so that you're publishing that it is 100% coverage. I am not saying that you are just like this. So I'm showing the legal way of doing things in consultation with designer.
Yes.
Yeah. So way to exclude, I showed here itself in the case. Otherwise, these should not be excluded. I agree with you. These are all not to be excluded. That's where very first option I said in my simulation, I go and then toggle my reset, and that will fix this problem, toggling of reset. And similarly, some states definitely they need to enter overlapping case, non-overlapping case. You just go and then just like how I change the stimulus, because initially what I was doing, I was giving only the pattern 101010 always, right? But what for some time continuously 0 comes, sometimes continuous 1 comes, or it goes out of sequence. All those cases, anyway, you do verification, right? As part of verification, you do automatically all those cases will be covered. So this is how you can analyze the coverage. And nowadays, all will give beautiful coverage reports in Excel. This is Linux environment. Not sure whether it will open in browser. But otherwise, they will give module by module, what is the coverage, and based on that, that's a management. You can submit that to the management. So in order to close the verification, or sign off the verification, you will use coverage metrics. You will use test case regression. All the tests are passing, and yeah. So these are the things what you use. And there should not be any bugs, open, or defects. We call those defects or the bugs in the design. Whatever you might have filed, this is one of the issue, and that issue should have been resolved by the time you close the verification. Yeah.
Okay, then it's over.
Yeah, coverage. That's all I can demonstrate at this point in time.
So,
Yeah.
Sneha madam, are you there? Sneha madam.
Yes, sir.
Shall we?
Yes, sir. Just a second.
So okay then. Just a minute.
Sir, should I share the screen?
Shivappa, shall I remove the sharing? Shivappa sir? It's done, no?
Yeah. No problem.
Oh, okay, just
Yeah, should I exit?
no, just a minute. Yeah, it's kind of vote of thanks to you.
Thank you.
Yeah,
Which
just a
one
minute.
need not be formal. Okay, thanks a lot.
No, wait. Yeah, 2 minutes. Just 2 minutes. Wait. So, thank you very much, Shivappa. I think Harish is also there.
Yeah.
Yeah, Harish is also there. And Swapnil is there? No, Swapnil is not there.
Sir, is it visible, sir?
Yeah. Yes. So, Shivappa, sir, thank you very much. This is a kind of a virtual trophy from our side, virtual certificate to you. Thank you very much for giving this session on digital design. And then I also thank Harish, ma'am, next.
Yeah,
Sneha,
thanks a lot. One specific correction. You put
Yeah.
Excel VLSI here. For both Harish and myself, Excel
I-
VLSI technology.
I asked to Entupal, but he said no, it has to be Entupal. I changed it actually from Excel to Entupal.
No. They don't know actually. Who Damodar
Acha.
said, is it?
No, Swapnil. And
No.
okay,
Swapnil doesn't know. Otherwise, I don't accept this actually because
okay.
Technology is our partner, and Excel VLSI Technologies, both Harish and myself are part of. So just
Acha,
mention that if you want to really, send it to us.
I will change it. And
Yeah.
then the Swapnil is there? No, Swapnil is not there. So he is the person who has arranged your sessions. So thank you very much.
Yeah.
Thanks a lot. Yeah, thanks a lot. So okay, so for participants now I have information. Other things are over. So I think Shivappa sir, you can leave. No problem. Thank you very much.
Yeah, thanks.
And Harish can also leave. It's okay. You are free now.
Yeah.
So yeah. So participants, we will have the session at 5 o'clock now. So 5 to 7, Naushad sir will be there. He will go. He will take us demonstration. So kind of a demo, and you can discuss with him. If you are new, already new the LT Spice, then good. But if you are new to LT Spice, then probably you can interact much more with him, and you can ask how to do analysis in detail, etc. Because he works on LT Spice too. Okay. So in evening session we will have LT Spice. Then tomorrow morning we will have Dr. Sudip Das Gupta from IIT Roorkee, and as such hands-on sessions are concerned, we will not have on cadence. So LT Spice and the electric. So that is, and Vivado also, we will take Xilinx Vivado so that the tool flow, chain flow is complete. That is, you will also have the synthesis, etc. So I will request Khandagade sir, who will be taking session, I think tomorrow evening. I will ask him to show the entire flow to you properly in Vivado, and he will do that. He is an expert in that. He will do it. Okay. And as far as today's morning video is concerned, some of you have told me that live link has not come there, and I have checked it. I don't know what mistake has happened technically in live streaming, but yes, I could identify that there was no record on the live stream morning session. So, but I have a record of this Cisco WebEx. So I simply downloaded that and I have uploaded it. Okay, so I have uploaded it on YouTube channel. So it is there. Okay, it's available over there. So, but then you will have to search it probably in the uploaded video. So, but you will get it there. I have uploaded it. Okay. And anything else you would like to ask? Otherwise, we will meet at 5. You can share with me anything else. Okay, nothing else. So we'll meet at 5. 5 p.m.
Hello, sir.
Madam, कौन है? Your name, please.
I'm Jayashree, madam. In case of any problems in handling cadence, whom you have to contact, sir? Online?
Swapnil.
Swapnil.
Cadence, you registered for something? You yourself have cadence, or you registered? What?
No, I have registered.
You registered, then immediately you should have told now, because then they will pay you the separate attention, separate session for you. They'll take. That's what they guaranteed.
Okay.
So I'll write his number here. Okay.
Okay.
I'll write his number. You can contact him.
Okay.
I'll write his number here. You call him directly.
Okay, sir. Okay.
राठौर सर।
हाँ सर।
कुछ नहीं, वो सवेरे मैंने आपको प्रॉब्लम बताया था कि मैं क्विज अटेम्प्ट नहीं कर पाया।
हाँ, मैं आपको व्हाट्सएप किया आपको।
यस, मैंने आपको रिवर्स किया है कि 330 और 345 इज ओके।
मैं देख लेता हूँ। ठीक है सर, ठीक है। लेकिन सर वो सिस्टम एडमिन ने देखा, उसमें सब ठीक ठाक था, पता नहीं क्या प्रॉब्लम।
पता नहीं, मैंने आपको किया, मुझे भी पता नहीं, क्योंकि हम भी मॉडल यूज करते हैं कॉलेज में, तो कभी ऐसा एरर नहीं आता, पता नहीं।
नहीं, वो भी बोले कभी आता नहीं। वो बोले सर कैसे हुआ नहीं। एक्चुअली मैं पूरा ब्रेक में वही काम कर रहा था।
ओके, नहीं वो आगे जा ही नहीं रहा था। जब भी वो नेक्स्ट क्लिक करता था, वो डायरेक्ट बाहर ही आ जाता था।
ओके,
तो पता नहीं, फिर मैंने स्नैपशॉट लेके रख दिया। मैं बोला एक बार
उसने क्या किया, मेरे सामने अटेम्प्ट किया वो क्विज। वो बोले सर मैं आपको उनके लॉगिन से अटेम्प्ट करके दिखाता हूँ। ही अटेम्प्टेड दैट एंड ही हैज प्रूव्ड कि यस इट इज हैपनिंग।
इवन सर मैंने अपने एडमिन से भी कांटेक्ट किया। मैंने बोला